Welcome to Calculus 1. In this lecture video, we're going to talk about the derivatives and the tangent line problem. Now recall, back in lecture video 2.1, we talked about the slope of a secant line is f of c plus delta of x minus f of c divided by delta of x. And as you can recall my drawing, as the point Q approaches to point P, the slope of the secant line will also approach the slopes of the tangent line. So when such a limiting position exists, what that tells us is that the slope of a tangent line is the limit of the slope of the secant line. Alright, so we can actually, what we can do is actually find using our limiting process. Alright, using the limiting process to find our derivative. I will introduce that just in a minute as well. So, definition of tangent line with a slope n. Let's say if my function f is defined on an open interval containing c, and if the limit, alright, of changing y over changing x as the delta of x approaching to 0, then the limits of the secant line will become the slopes of the tangent line. Alright, so if such limit exists, then the line passing through c comma f of c with m as with the slope m is the tangent line to the graph at that point. Okay, so back to the picture again. When such limit exists, okay, when such limit exists at that point P that I mentioned it before, which is c comma f of c, alright, then the slope of my tangent line here that I drew, alright, this slope m will be the slope of the tangent line for this entire function. Alright, at that particular point. Alright, so this is a very interesting problem here, kind of explaining how this limiting process can help us. If I want to find the slopes of the tangent line to this graph at point 2 comma 4, alright, so I'm going to let c comma f of c representing an arbitrary point on the graph. Alright, so this point is an arbitrary point on the graph of function f, which is my function x squared plus 2. Then the slope of a tangent line at an arbitrary point will be given by, alright, let's try this. Alright, so if I use the formula, the limit of the function as delta x approaching to 0 of f of c plus delta x minus f of c over delta of x. Alright, so if I use this formula, okay, eventually the limits will become the slope of the tangent line. So here I will substitute c plus delta of x, okay, for x. So wherever I see x in my function, I will put c plus delta of x. So that will give me, let me write this part down real quick. Alright, that will give me c plus delta of x squared plus 2. And that, alright, so this part is the same as f of c plus delta of x minus f of c. That means I will substitute c for every x I see in my function. So that will be minus c squared plus 2 over delta of x. Alright, if I simplify my numerator, c plus delta of x whole thing squared, using my perfect square binomial, that should leave me with c squared plus 2c delta of x plus delta of x squared. Okay, perfect square binomial, a plus b whole thing squared is a squared plus 2ab times b gotta be squared plus 2 minus c squared minus 2. Whole thing over delta of x. Alright, so if I simplify this, I believe the c squared will cancel out. The 2 will cancel out. So that leaves me with 2c delta of x plus delta of x squared. Now since the 2 term left on top, both of them have delta of x, I can actually factor out delta of x. So if I factor out delta of x, what's left will be 2c for this term plus another delta of x. Alright, over delta of x. And the delta of x, top and bottom, will cancel out. So what left on top is 2c plus delta of x. So as the limit of 2c plus delta of x, as delta of x approaching to 0, that means this term will actually become 0. So that means my limit of the function will only end up with 2c. Then what does 2c represent is the slope of the tangent line at any point. Okay, at any point c comma f of c. So at the particular point 2 comma 4, alright, so that means the 2 is my c, the 4 is my f of c. Because if you plug in 2 for x, 2 squared plus 2 will be well, as a matter of fact, it's actually 6, I'm sorry, 2 squared plus 2. So sorry about that. That's supposed to be a 6 right here. That's my fault. Alright, so this is c comma f of c is 6. So what is the slope at this particular point? The slope at that particular point, since 2 is my c, the slope at that particular point 2 comma 6 will be 2 times 2, which will give me 4. And I can actually evaluate slopes at any given point, okay, on this x squared plus 2. But the slope at this particular point will be 4. So we know x squared plus 2 is a parabola. Okay, we got a 2 comma 6 as one point. I can also have a negative 2 for x, and I can actually evaluate my slope at that negative 2 comma something at that particular point, which is another 2 times c. Alright, very interesting, very, very interesting. We can actually evaluate slopes of the tangent line at any given point on this continuous function. Real quick, just in case this thing comes up, if my function f is continuous at c, the limit of the secant line here becomes infinity or negative infinity. In other words, if my slope becomes infinity, if the slope of my tangent line becomes infinity or negative infinity, then there's going to be a vertical line x equal to c passing through, okay, my arbitrary point c comma fc. Okay, then we call that the vertical tangent line. All right, once in a while this thing will pop up, and I believe I have one example I will show you. So it turns out the limit used to define the slope of a tangent line is also used to define one of the most important operations of calculus called differentiation. All right, so the derivative of my function f at x, at my point x, is given by f prime of x is equal to the limit of f of x plus delta of x minus f of x over delta of x, as the delta of x approaching to 0. So the process of finding the slope, the limit process that we use to find slope of a tangent line, is actually the same as the derivative, okay, of a function at x. So what that tells us that is the limit, okay, the concept of limit actually, promotes the derivative of a function. It promotes the derivative of a function. Alright, differentiation is the process of finding the derivative of a function. A function is differentiable at x if its derivative exists at that particular x, and differentiable on an open interval from a to b if it is differentiable at every point in the interval. Okay, that's what differentiation is. It's a process of finding the derivative of a function, and a function got to be differentiable at x. If the derivative also exists at x. Alright, common notations for derivatives. I can say f prime of x, I can say dy over dx. Dy over dx means derivative of y in respect of variable x. I can say y prime, I can derivative of the function in respect of x, or I can say derivative of x, y. Okay, because I can let my y equal to my function. So these are just a common notation that that we use in calculus classes. All right, so to find the derivative of a function, is the same thing as the limiting process. Okay, finding the slopes of a tangent line. It's exactly the same thing. Alright, let's try and see if we can find a derivative of a function by the limit process. So I'm going to go back and use this formula right here rather than using c, okay, finding the slope at a particular point. Alright, I'm actually going to find derivative of x. I'm changing my c to a variable x here. Alright, so let's find derivative. F prime of x will be the limit of f of x plus delta of x minus f of x over delta of x, as delta of x approaching to 0. Alright, so I will substitute the x plus delta of x into whatever x I see in my function. So when I first write it out, if I want to first write it out, that's an x right there. There will be limits of 2 times x plus delta of x to the 3rd power plus 3 times x plus delta of x squared minus f of x, and this is f of x, so I will minus 2x to the third plus 3x squared. Alright, whole thing over, delta of x. As the delta of x approaching to 0. Alright, so this is quite a bit of work if I want to multiply this out. Especially right here. X plus delta of x to the third power. That's quite a bit of work. We know that x plus delta of x squared, alright, x plus delta of x squared that will give me x squared plus 2x delta of x plus delta of x squared. Alright, so if I got third power, that means I got to multiply another x plus delta of x. So this whole thing here will multiply another x plus delta of x. Alright, so let's give that a try real quick. So x squared times x, be x to the third. X squared times delta of x, positive x squared delta of x. Alright, 2x delta x times x, that will be 2x squared delta of x. 2x delta of x times delta of x, that will be 2x delta of x squared. Delta of x squared times x, positive x delta x squared, and delta of x squared times delta of x, delta x to the third. Alright, let's see if I got any like term to combine. X to the third, no like term, so still x to the third. X squared delta x, 2x squared delta x. That's it. So that make it 3. 3x squared delta of x. So I'm done with this. I'm gonna scratch them off. Alright, 2x delta x squared plus x delta of x squared. So that make it 3 again. So that would be 3x delta of x squared plus delta x to the third. Alright, so all that is my answer. All that is my answer for what I highlighted here. Alright, remember there's a 2 times up front of it. So let me copy and paste real quick. So I'm going to put it right here a little bit. Make it a little bit smaller. A little bit too big. Alright, so all that, with the limit of delta of x in the front here, I got a plus. So all these times by 2 plus 3 times x plus delta x squared, that will be x squared plus 2x delta of x plus delta of x squared minus 2x to the third. So I apologize here. That's 3x squared and then the parenthesis. My fault. Minus 3x squared. Alright, let's see if we can combine some like terms here. Everybody's over delta of x. Alright, 2 times x to the third. 2x to the third plus 3, 2x to the third minus 2x to the third. That cancels out. Let's see what else can be canceled out. A lot of things should cancel out pretty nice. 3x squared. Alright, right here. 3x squared minus 3x squared. That cancels out. Alright, let me distribute. I'll go ahead and get rid of those so it's a little bit easier to look at. If I now distribute my 2, and then the next term distribute the 3, then I will have the limits delta to x approaching to 0. Let's see, the 6x squared delta to x plus 6x delta to x squared plus 2 delta x to the third plus 6x delta of x and 3 delta to x squared. Okay, everybody over delta to x. Alright, since every term has delta of x up top, we can actually factor out a delta of x. So the limits delta of x go to 0. 66263. Oh, this is not 2. That's supposed to be a 6 right here. Never mind, we were right. It was 2. 2 times 3, 2 times 3, 2 times 1 right here. I'm gonna make sure my math is right. Don't want to make a mistake here. Let me go back and check over here. Delta x to the third. Yep. That's correct. Make sure I canceled out everybody, right? Two x to the third. Mr. Jim made a mistake somewhere. 6x delta to x 3 right there. I guess I'm right. I guess there's no mistake here. Alright, so what that tell me is I thought I could factor out a 3, but I cannot unless I have somebody I can combine with, which I don't have anybody to combine with. So I can factor out a 2. If I factor out a 2 out, what that will leave me with, a 2 and a delta of x. Every term has delta of x. So that will give me 3x squared plus, this is going to be 3x delta of x plus delta of x squared plus 3x. Oh, I get, it's alright. 3x, because this delta x goes to the outside, plus if I factor it out, it would be 3 half. So perhaps I shouldn't factor out a 3. Let me just leave this coefficient here. I wanted to factor out a 3. It's almost like I wanted something to happen, but it's not gonna happen. I have something in my mind I wanted to happen, but it just ain't gonna happen. Alright, 6x squared. This delta x goes to the outside. This will be supposed to be 6x delta of x plus 2 delta of x squared plus 6x plus 3 delta of x. Okay, delta x squared, one of them go out, the other one stays in. It doesn't really make a difference what I really wanted to factor out, or what coefficient I wanted to factor out, because what's going to happen is the delta of x will cancel out on the out here. So what I left in here as the delta of x approaching to 0, this term will become a 0 term. This term will become a 0 term. This term will become a 0 term. So what I will still end up is the answer itself, 6x squared plus 6x. There you go. So this will be the derivative, okay, of this function. And this is also, okay, the slope of a tangent line, and we, at any arbitrary point, c comma f of c, and I can evaluate it at any point. All right, that one was a lot of work. Let's try another one. All right, same process. Okay, find the derivative of the function by limiting process. I got to start off with like this. Gotta start off with my definition here. So I got to substitute x plus delta of x for every x I see in my function. So that will tell me is this is going to be 5 over this spot going to be x plus delta of x, then minus 4 minus the function itself, which is 5 over x minus 4. Alright, whole thing divided by delta of x. Alright, so let's simplify this rational expression here. My LCD is the 2 denominator itself, okay, plus the actual denominator of the entire function. So what I can do here is multiply my numerators and the denominator by the 3 denominator here listed. So that will be delta of x times x plus delta of x minus 4 times x minus 4, top and bottom. Alright, so if I multiply the top and bottom by the LCD between all of these fractions, okay, so this denominator is missing delta of x and x minus 4. So basically what's going to happen is the x plus delta x minus 4 will cancel out to leave me with delta of x, x minus 4, and times the 5. So there will be 5 times delta of x times x minus 4 minus 5 times, alright, this denominator x minus 4 will cancel out right there. That will be left with delta of x times x plus delta of x minus 4. Alright, whole thing over. is delta x times x plus delta x minus 4 plus x minus 4. Okay. Alright, let's multiply this top out here real quick. I'm not going to do the bottom. I want to simplify for the top, because what I have in mind is where I got lots of delta of x up top, and then eventually I can factor them out and then cancel it out with the delta of x down here. Okay, somehow, some way, something got to cancel. Okay, so I can apply. Therefore, I can apply delta x as x approaching to 0. Right now, this delta x got to be canceled out. Okay, for that to happen. So let's multiply it out. 5 delta x times x. It'll be 5x delta x minus 20 delta of x. Alright, negative 5 times x, negative 5x delta of x. Oops, minus 5 times delta of x squared plus 20 delta of x. Alright, everybody over the LCD. Alright, let's see what can cancel out here. This two term cancels out. And this two term cancels out. I think I made a mistake up here. I think this delta to x times that delta to x will give me delta to x squared. There you go. That'll work. So the only term left up top, delta to x squared, delta to x squared cancels out, because there's one term on top over one term in the bottom for the top and bottom to cancel out. So what I really got to have left is really just a negative 5 up top over the x plus delta to x minus 4 times x minus 4. So as delta of x approaching to 0, that means this term is going to be a 0 term. So that leaves me with x minus 4 and x minus 4 in the denominator. So my answer will be just negative 5 over x minus 4 whole thing squared. Okay, that will be my slope. All right, a little bit easier, because what works out for us is things will cancel, or things can be factored out, where my denominator can, my delta x in the bottom can be canceled out. Now let's try one more before we talk about another concept. Alright, start out with the same process, okay? X plus delta x, put it right here where the x is in my function. So what I'm going to have here is a square root of x plus delta of x, then I'll go plus the 3. Alright, minus my function itself, x plus 3, over delta of x. Alright, so let's rationalize my numerator here. So I'm going to conjugate. So to conjugate, that would be multiplying the same thing, except rather than a minus, I will actually multiply with a plus here to conjugate. So I will multiply square root of x plus delta of x plus 3 plus square root of 3, top and bottom. So I can conjugate. Rationalize my numerator. So what that will create for my top is a difference of squares. This is a minus, that's a plus. So if I create a difference of square, that tell me that it will simply be, a minus b times a plus b. A minus b times a plus b. Difference of square will simply be a squared minus b squared. That's what I conjugated. So that will just leave me with this whole thing squared. Okay, this whole thing squared minus that thing squared. So that will just actually cancel out my square roots. So that will be this minus my x plus 3 when I conjugate it over my denominator. I'm not going to multiply this out. It would just be delta to the x times my square root of x plus delta to the x plus 3 plus square root of x plus 3. Alright, if I simplify the top, I believe this x minus that x will cancel out. 3 minus 3 will cancel out. Only thing left on top is delta to the x, and delta to the x in the bottom, delta to the x can cancel out. Because one term over one term, delta to x can cancel. So now I apply the limit. That means this term will become a 0 term. So the only thing I got left on the numerator is 1 over square root of delta to, square root of x plus 3 plus another square root of x plus 3. So that will make it 2 square root of x plus 3. There you go. That's my answer. There's 2 of them because here is 1, here's another one. So 1 plus 1 will be the 2. Alright. So that's how we use finding the derivative using the limiting process. Alright, there's an alternative form of derivative. Okay. The alternative form, the derivative of f at the c, at the point c, will be f prime of c as a limit of my f of x minus f of c over x minus c as the x approaching to c. So using the graph, it kind of makes sense. I'm just changing my notations here a little bit. If we go back to the drawing from before, this is x plus delta of x here. Alright. So c plus delta of x right here, where does that really come from? Because from the point c, from this x value to that x value, okay, excuse me, yes, that's right, from this x value to that x value, to reach there, I can just adding the change. I can add, the differences, and I show it to y'all. If this is, if this is 1, this is 4, then the change between the two will be 3. Therefore, go from C1 plus 3 will actually reach the x value for point Q. Alright, rather than using delta of x, okay, changing notation, I'm just going to say x minus c. Alright, go from this point to that point. The difference in the horizontal will be this x value, which is bigger, minus the c. And then changing in altitude, changing the y direction, that will be f of x minus f of c. Okay, you're just subtracting them. So that will be the alternative form. Alright. So the existence of the limit in the alternative form requires that the one side limit exists and equal. So the limit from the right and the limit from the left still got to equal to each other. Okay. If it does not equal, that means the limit does not exist. If the limit does not equal, that means the function is not differentiable at that particular point. And I will show you an example just in a minute. So a function f is differentiable on the closed interval from a to b if it is differentiable on the open interval from a to b. And if the derivative on the right at the a and the derivative on the left at b both actually exist. And I believe we're explaining that concept using using a graph from -1 to 1. Okay, continuity. I think the graph would look something like that before. So it's basically the same concept. Okay, except now we're just adding what? We're just adding the differentiable part. Okay. If you're continuous in a closed interval, that means your function is also differentiable on that closed interval. Now what I translate into is problem like this one. Alright, so I'm gonna say x is at 2, and I want to find f prime of 2 using the alternative form. So check it out. Alright, this is the alternative form, and this is coming from the left. Alright, so for this absolute value function, okay, f of x is my absolute value of x minus 2. So absolute value of x minus 2 minus f of c. If I plug in c in here into my function, 2 minus 2 is 0, over x minus c, which is x minus 2. So this function here, if I put it in the graphing calculator, math, absolute value of x minus 2, close parenthesis, divided by x minus 2. Alright, approaching to 2 from the left, the y value is actually -1. Approaching to 2 from the right, the y value is actually +1. So everything's the same, except this time this limit is coming from the right, which is 1. So my limit is not the same from both directions, therefore my limit does not exist. Alright, so if my limit does not exist, that means my function f is not differentiable. What that tells me is my function f is not differentiable at x equal to 2. Alright, what I mean is I do not have a tangent line at this point 2, 0. Okay, I do not have a tangent line at that particular point. And the graph kind of shows it too as well. Alright. Tangent line does not exist because the limit from both directions is actually not the same. Got to be the same for the function to be differentiable at that particular point. Alright. Let me show you another example using the alternative form. X to the 1/3 power. It's a very weird looking graph. So if I would use the same process, well, I want to find f prime of 0. Alright, f of x So the limit of x approaching to 0, c is my 0 from the negative side. Okay. X to the 1/3. Alright, over x minus c. Well, c is 0, so I can just write just minus x. Alright, let's see what that is. And let's do the other one. Limits of x approaching to 0 from the positive side of x to the 1/3 over x. Alright, let's see what happens here. By the way, x to the 1/3 over x is the same thing as x to the negative 2/3. You know, 1/3 minus 1, negative 2/3. So in my graphing calculator, I'm simply going to type in x raised into the parenthesis negative 2/3. Alright, I'm going to shrink this a little bit so we can see a little bit better. I'm going to do from negative 5 to 5 for my x. Alright, coming from the left, approaching 0. Okay, I'm actually going up, 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 up because I do have a vertical asymptote at 0. Coming from the right, I'm doing the same thing. So both limit will actually be infinity. Okay. So remember earlier, a while back, if the limit, where is it? Let me find it. All right. If f is continuous, which is continuous. All right. If the limits as delta of x approaching to 0, okay, is equal to infinity or negative infinity. Alright, that means there's a vertical line passing through, okay, my point. Therefore, there's a vertical tangent line. So what that tells us is there is a vertical tangent line at x equal to 0. Alright. Therefore, if there's a vertical tangent line, that means my f is actually not differentiable at that particular point 0. Okay. Not differentiable. Because you got to think about it. Yeah, I do have a tangent line here from this function, but what I type in is actually x to the negative 2/3. So my function is continuous. Okay, my function is continuous, but because there's a vertical tangent line, that actually tells me that my function is not differentiable at x equal to 0. All right. So what this implies is kind of strange. Differentiability implies continuity. What it's saying is if the function is differentiable at x equal to a particular number, then the function will be continuous at that same number. But it is possible for a function to be continuous at that particular point, but not differentiable at that particular point. So continuity does not imply differentiability. But vice versa, differentiability implies continuity, just like this problem here. Okay, my function, at 0, for my function, it is continuous at 0, but my function ended up to be not differentiable at 0 because the vertical tangent line here. All right, so hopefully we have a better understanding of derivative and the limit process. Okay. The limit process, okay, inspires derivatives. That's basically what this lecture video tells us. So the next time when we do derivatives, we're not going to go through the limit process again. Okay, we're going to actually use a different way we're gonna directly. We can find the derivative without using the definition limit directly. Alright, that will conclude this video. Thank you for watching.